Okay, in this video, I want to present a proof of the chain rule. And there are videos on the internet that give a proof of the chain rule. Any good calculus textbook will have a proof of the chain rule, but at least online, a lot of the proofs are not correct. They're either, for instance, on the Khan Academy video on the chain rule, the proof is not completely correct. They only prove it in a special case. And there are also videos, I'm sure, where people give intuitive ideas of the proof, but it's not a rigorous proof. They just give kind of plausible explanations of why the chain rule ought to be true, or why it is plausible that the chain rule is true, but that's not the same as a rigorous proof of the chain rule. A rigorous proof would be a step-by-step list of assertions that are backed up by logic and that imply the theorem that we're trying to prove. And some of the kind of plausible quote-unquote proofs, they're not really proofs, are something like, if you have two functions f and g that are differentiable, then they're approximately linear, and so the composition is approximately linear, and if you work with the linear equations, then the statement turns out to be true, so it's true for the composition. Something like that. But that has a gap in the argument, which is that it was never stated what exactly it means for a function to be approximately linear. I mean, that is swept under the rug. So it's not a, it can probably be adapted into a correct proof, modified into a correct proof, but it's not a rigorous proof. Okay, so in this video, I want to present a rigorous proof, which is completely correct and isn't, I'm not sweeping anything under the rug. But the proof ends up being a bit complicated, as we'll see. Okay, so let's just introduce some notation. So what we're trying to prove is the chain rule, which is that if you have two differentiable functions, f and g, I'm not going to be super precise about it, about, the domain of f and g. I'm just going to assume that f and g are differentiable everywhere. Then if you have x0, say in the domain of g, and you have two differentiable functions f and g, then the derivative of f of g evaluated at x0 is equal to f prime evaluated at g of x0 times g prime of x0, right? That's the chain rule. Okay, so that's what we want to show. And so we have to find a way to take the left side and make it equal to the right side, or to take the right side and make it equal to the left side. So let's take a look at what each side is by writing it in terms of limits. So we have f of g prime of x0. Well, that's the derivative of f of g evaluated at x0, and that by definition is the limit as x goes to x0 of f of g of x minus f of g of x0 divided by x minus x0. Okay, that's just the definition of the derivative. You may have learned the definition of the derivative with the, f of x plus h minus f of x over h, but it's an equivalent definition. I'm just using x goes to x0 instead of h goes to 0. Okay, hopefully you're familiar with this alternate definition of the derivative. It's essentially just the same with different notation. Okay, but I think this is a little easier to work with than the definition with h. going to 0. All right, that's the left-hand side. Now what's the right-hand side? So the right-hand side is f prime of g of x0 times g prime of x0. Well, g prime of x0 is easy. That's, by definition, the limit as x goes to x0 of g of x minus g of x0 over x minus x0. Okay, that's just the definition of g prime of x0. And what about the definition of f prime of g of x0? Well, you see, I want to use x going to x0, and here the thing inside f prime is g of x0. So I'm going to use a different letter. I'm going to use u. So it's the limit as u goes to g of x0 of f of u minus f of g of x0 over u minus g of x0, right? So the goal is to show that this is equal to that. Well, let's take a look at, by the way, the proof of this is not obvious. Okay, I think you should, try to follow it, but you're not expected, or at least I wouldn't expect you to be able to come up with this. Okay, so let's just look at this function where the limit of this function is considered where u goes to g of x0. So this function in green, okay, this function, f of u minus f of g of x0 over u minus g of x0. The function f of u minus f of g of x0 over u minus g of x0. Notice that this is not defined when the denominator is 0, right? It's not defined at u equals g of x0. So the idea behind this proof, before we keep going, is we would like to work with this limit. We want to say something about this limit, and to do that we have to work with this function. And it turns out that it'll be helpful to work with this function composed with g. Because if you had that, you would have like f of g of x here, and then you would have g of x here. So you would get something that looks like f of g of x minus f of g of x0 over g of x minus g of x0, which is what you have. You see, if you had that, right, if you had this, and then you multiplied it by that, you would get this. So that's the idea. But the issue with working with this limit directly, right, the reason why it's hard to work with this is that this function here is not defined at u equals g of x0. And we want it to be defined. The idea is to use this property of continuous functions, that when you have a composition of continuous functions, that is a continuous function. But of course, it doesn't work if your function isn't defined. So this function is not defined at u equals g of x0. But what we can say is we know its limit What is the limit as u approaches g of x0? Well, by definition, that's equal to f prime of g of x0, right? That's what we just talked about. The limit of this function, that's this, is equal to this. And so there's this kind of trick. How do you have this point u equals g of x0 where this function is not continuous. It's not defined there. But the limit exists. So what you can do is you can just, what's going to happen is like there's a hole in the graph. And you can, if you define the function to be that limit, then you remove the discontinuity. Right? The function will be a continuous function. So we define And this is a function of u, right? So let's define a of u to be this function f of u minus f of g of x0 over u minus g of x0 if u is not equal to g of x0. And if u is equal to g of x0, we'll define it to be the limit of that function, which is f prime of g of x0. Well, with this definition of a, then a is continuous at u equals g of x0. And therefore, a composed with g is continuous at x equals x0. Okay, let's clarify why that's true. So g is a differentiable function at x equals x0. And a function that's differentiable at x equals x0 must be continuous at x equals x0. That's a theorem that differentiability implies continuity. And then you have this fact that if you have a is continuous and g is continuous, the composition is continuous. So that's where this fact comes from. Now, what does it mean to say that a composed with g is continuous at x equals x0? What it means is that a of g of x0 is equal to the limit as x approaches x0 of a of g of x. Right? That's just the definition of continuity. And what's a of g of x0? Well, if you look back at the definition of a of u, just plug in g of x0. Well, that's u equals g of x0. And it says if u is equal to g of x0, a of u is that. So a of g of x0 is equal to f prime of g of x0. Okay. So just to clarify, this first equation, that's just from the definition of a, but the fact that a of g is continuous at x0 gives you this equation. By continuity of a composed with g. Okay? So once we have that, let's go back to let's see. Let's take a look at this expression. All right. So we want to work with this, and we want to, in particular, to work with this numerator. This numerator is kind of hard to work with because you have a composition f of g, and we're really trying to break up the limit into a product of two limits, right? Because we're trying to make that limit equal this product. So with that in mind, we have this useful fact, which is that, so we have, okay, the claim is that f of g of x minus f of g of x0 equals a of g of x times g of x minus g of x0. Okay, let's see why this is true. So this is true because this is true for all x, because if you have an x for which g of x is equal to g of x0, well, what happens if g of x equals g of x0? This thing will be 0, right? And so this whole right-hand side will be 0. And why is the left-hand side equal to 0? Well, if g of x is equal to g of x0, then, I mean, you just have f of that minus f of the same thing, so you get 0. So therefore, it is in fact true if g of x equals g of x0. If this is the case, then both sides equal 0. Okay. And what happens if g of x is not equal to g of x0? Suppose that x is such that g of x is not equal to g of x0, then what happens? Why is the left-hand side equal to the right-hand side? Well, that follows from the definition, right? Because in that case, a of g of x is going to be that f of g of x minus f of g of x0 all over g of x minus g of x0. Then you multiply both sides by the denominator, and then you get this equation. So it's true no matter what. So if g of x is not equal to g of x0, then this equation follows from the definition of a of g of x. Okay, so why is this useful? Let's put it in purple. This is a useful equation because we can use that to evaluate this limit. Because, see, you have this numerator. That's the numerator. The numerator is what's showing up here. And now we've written that as a product of two things, which is good because then we can use our limit facts. So let's put it all together. So we have f of g prime of x0. I'm just rewriting it. I wrote this already, but it's the limit as x goes to x0 of f of g of x minus f of g of x0 all over x minus x0. And this is equal to, by the fact in purple, I should say x goes to x0, we can replace the numerator by a of g of x times g of x minus g of x0. And then I just keep the denominator the same. And then the benefit of this is that I have a product. I have, see, this thing, okay, this thing, that's a of g of x times that, right? And when you have two functions and you're finding the limit, you can split it up into the limit of each function and then multiply those limits together as long as the limits of the individual functions exist. And so let's write this as the limit as x goes to x0 of a of g of x times the limit as x goes to x0 of g of x minus g of x0 over x minus x0. So I have this times this, provided that the limits exist. But do the limits exist? Well, what's this limit? It's g prime of x0, right? This is equal to g prime of x0. And then on the left, what is this limit? Well, we already found that above. It's here. And we showed that that's equal to f prime of g of x0. So what have we shown? We've shown that f of g prime of x0 is equal to that, which is the chain rule. So that's the proof of the chain rule. Okay, let's just review the key steps because that was a lot. And this isn't the only way to present the proof, but it's the way that's probably one of the simplest ways to present the proof. So first, of course, we just write out what the left and right hand sides are equal to in terms of limits. That's this. And then the insight is we have to think about this function. And this function, f of u minus f of g of x0 all over u minus g of x0, this is a function of u. It's not defined when u is equal to g of x0 because the denominator is equal to 0. But the limit exists. And so we define this new function a of u, which is continuous at u equals g of x0. And when you write out, and since a is continuous, a composed with g is continuous at x0. And if you just write out what that means, you get that the limit of a of g of x is equal to f prime of g of x0. Okay, so that was the first key step. And then the second key step was to show this equation in purple, that you can rewrite the numerator here. This numerator can be rewritten in terms of a of g of x times g of x minus g of x0. And then once you do that, then this whole thing equals this, and then you can split up the limits, and then you can plug in what we had found above, that the first limit is f prime of g of x0, and then we know by definition that the second limit is g prime of x0. And that's the proof. Okay, so what can we say about this proof? It's somewhat complicated, right? It's probably more complicated than the proof of the product rule or the quotient rule, but I mean, it works. I think the hard part is just getting a grip on the composition, right? I mean, because you have x going to x0 and then u going to g of x0. And the key idea, I think, was once you have this function a of u, to notice that since a is continuous, this composition is continuous, and that allows you to work with the limit. Okay, so I hope that this video is helpful, and thanks for watching.